So I've copied this from page 264 of Lister and Renshaw's excellent book on A-level chemistry. The story here, if we just start in the middle, this is just the Born-Haber cycle for calcium fluoride. So we start off with calcium fluoride solid, CaF₂, and then CaF₂ is made from calcium and fluorine elements in their standard states, so delta HF there. And then if I want to go around the long way, well, I need to atomize calcium to make calcium gas, and then I need to ionize calcium once and then twice to make calcium 2+ ions, gas phase, and the electrons. And lastly, I need to atomize fluorine, because atomization gives us 1 mole of fluorine atoms. We need 2 lots of that delta H to make fluorine on the top. And then coming down, I need 2 lots of the electron affinity for fluorine to make the 2F- gaseous ions. And now we can drop down to calcium fluoride for the lattice formation enthalpy of calcium fluoride. Okay, perfect. So let's ask the question, why does calcium fluoride make CaF₂ and not, say, CaF? Might seem like a bit of a pointless question, but hang in there. Let's do the Born-Haber cycle for CaF. Well, okay, so we need calcium and half a fluorine molecule here to make CaF. Notice that the delta HF is not quite as big for calcium F as it is for calcium F2. Of course, going up here, we still need atomization of calcium. We need the first ionization of calcium, but we don't need the second one because we're only making 1+ ions of calcium. We're still making a fluorine gas atom, so atomization of fluorine, although we only need 1 mole this time, and then we only need 1 mole of the electron affinity to make 1 mole of F- ions, and now we'd have the lattice formation enthalpy calcium fluoride. So the Born-Haber cycle still works, but because calcium fluoride is kind of hovering up here, if we compare that with calcium and fluorine up there and calcium F2 down there, we can see that thermodynamically it will be downhill, exothermic, for calcium F to form itself into calcium F2 and a little bit of calcium metal. In fact, we can do the Hess cycle for it, and if you look in the Lister and Renshaw book, there it is. Okay, great. So calcium CaF is not thermodynamically stable compared with CaF₂. If we had any calcium F, if we managed to isolate a sample of CaF, it would very quickly decompose into CaF₂ and elemental calcium. So it won't work. The numbers don't add up. But what if we wanted to make CaF₃? Okay, so follow with me here. So 3/2F2. I still need to atomize a mole of calcium atoms. I still need to ionize. So this would be the first ionization energy here. So calcium plus. And then ionize again. So this would be the second ionization energy, up to calcium 2+ and 2 electrons. And then, of course, I'll need the third ionization energy. Talk about off the charts. So the third ionization energy is going to take us way up, because, of course, the first 2 electrons come out of calcium's outer shell fairly easily, that 4s outer shell. But the third ionization energy, now we're breaking into the third shell, the 3p, which is going to take a huge amount more energy. So, whoa, we're right up there. And then we have to add to that the atomization of 3 fluorine atoms, so 3 moles of that. And then I'll come down a little bit when I have 3 lots of the electron affinity for fluorine. So we'll end up here with a calcium 3+ ion, gaseous ion, and 3 lots of F-. Okay, so fair enough, we did get there. But now when I make the lattice, I end up here, CaF₃ solid, which, as you can see, is endothermic with respect to the elements. So because it takes a huge amount of energy to pull that electron out of calcium's third shell, and I don't get that electron, that energy back when we make CaF₃, that means that I'm kind of, it's like you know, your expenditure over the month is far more than your earnings, and at the end you're left with this huge deficit. You're in debt at the end of each month because you simply don't have the energy to get to CaF₃. So we can see that both of these, CaF is thermodynamically unstable with respect to CaF₂ and calcium, and CaF₃ is even harder to get to because the delta HF would be positive. We don't have enough energy to make it stable, and that explains in a very kind of roundabout thermodynamical way. Is that a word? Thermodynamical? I think it should be. It explains why calcium F2 is the go-to lattice of choice for calcium and fluoride. We don't get any CaF or any CaF₃.